Good evening and welcome to another live stream. Tonight we're going to be looking at a bit of an issue that I'm trying to resolve. We had a bit of a mishap, so we're currently in recovery mode, but that's good because it means there is plenty of opportunity for learning. I did a live stream on Twitch and I was putting together my low voltage controller, and we had a bit of a mishap. We had a bit of a problem. What sort of a problem? Well, we managed to destroy at least two components. The first of which was a voltage regulator. The next was an ESP8266. And after the stream, I did an attempt to try and find what the problem was, and I'm probably have destroyed a capacitor. So let's get into this. This is not going to be pretty, but that is the joy of learning by doing. That is the joy of iterative prototyping, and sometimes you just got to break some eggs. Hey, Dimitri. Row Rally Race, welcome in. How you doing? So I am live streaming on both Twitch and YouTube. So if you see me responding to a question that is not on your platform, that is because it's coming in for the other one. So if you're on YouTube and you see me speaking to somebody who's not there, I'm talking to somebody on Twitch, and vice versa. If I'm talking to somebody and they're not there on Twitch, I'm talking to somebody on YouTube. Just to clarify what the configuration of the setup is tonight. So let's get and have a look at the damage, shall we? It's a bit ugly, but that's fine. That's just the way it is sometimes. Let's get this microscope up high, and we've got the board in a vise. So this is one of my circuit boards that came from PCBX. I've taken delivery of the first order from PCBX, and I have to say, I'm pleasantly surprised with the quality. Here is the said board. All right, it's a 4-channel controller. And there's some pretty decent sort of silk screening going on. There's some really tiny text on here. So yeah, these boards are pretty nice. I like them. Unfortunately, I've destroyed one, but that's what happens with rapid prototyping. So let us quickly take a moment to savor how we got here, right? So I did a live stream on Twitch and I was putting the components together. I was powering up, and then this happened. So just in case you missed that, let's do that in slow motion. And in case you missed that, let's go close. There goes the magic smoke. The spell was cast. The magic smoke was released. And in that moment, we destroyed a voltage regulator and an ESP8266. So what is the cause of this? So let's get a few things out of the way here, right? Let's set us up for this evening's activities. So I have got a series of low voltage regulators, or LDOs, They're low dropout voltage regulators. And these modules, let me just bring this under the spotlight on the microscope. It would help if I chose the microscope scene. There we go. These are 3.3. Was that by design, a smoke machine? Unfortunately not. So these are 3.3 volts voltage regulators. According to the data sheet, they should be tolerant up to, I think, about 16 volts. And we were providing these with a 12-volt supply. Now, I first thought the problem was that so we've got a couple of pins here, right? Let me get a pointing device. I don't know if this is going to be too big. Right, so we've got a voltage in pin on the bottom left. In the center, we have a ground pin. To the right, we have a enable pin, and this turns this voltage regulator on and off. The top left pin up here is the 3.3 volts output. And then there's this final pin, this fifth pin on the top right. And in this package, it is actually not used. So it's not connected, but it can be used for a voltage selection. You can use a couple of components and you can manually set the voltage of this device. But this variant of this regulator, it doesn't require it. It's set to 3.3 volts. So what is a voltage regulator? A voltage regulator is a component that takes a higher voltage and it drops it down to a lower voltage. So for example, we can put 5 volts in and get 3.3 volts, or we get 12 volts in and we get 9 volts in, right? So what we're attempting to do here is power our low voltage controller from a range of voltages from 5 volts all the way up to 12, maybe even higher volts. The problem that it seems is that the data sheet for this particular voltage regulator was telling porky pies. It was telling lies. So I used this particular voltage regulator because it was a small package for starters. So it can put it onto a board and hide it away somewhere, and it keeps your overall project relatively small. The next thing that this has is that it's 3.3 volts, which is perfect for microcontrollers such as the ESP32, the ESP8266. So it's ideal. And the low voltage dropout element of this means that I can be less than half a volt above 3.3. So I can be like 3.8 volts, 3.7 volts, somewhere in that region. And the device will keep running, which is absolutely perfect when using a lithium ion cell like an 18650 or a LiPo, which have a nominal voltage of around 4.2 down to about 3.8. So this is perfect. If you have a more heavy-duty voltage regulator, what can sometimes happen is that the voltage will drop out before you reach the depletion of the battery, so you don't get full range of the battery. Now, in this use case, we are not using a LiPo battery. We are using a wall power supply, giving us 12 volts for my lights. So I'm going to swap out the voltage regulator with a different model, but unfortunately, this model has a completely different footprint. So we're going to have to experiment with it, first of all, to make sure that it's not going to destroy the ESP8266 when we come to assemble it. and we need to make sure that, you know, things are going to work well for us. So if you have any questions as we're going along, please feel free to ask. I live stream to share my knowledge, share my experience, good or bad. Hence, we're getting to the point of recovery here. Our project has just died. What are we going to do about it? So we've done step one. We've talked about what the problem is. How did it destroy my ESP8266? Well, as it decide to eat itself, if I can get this video to play, as this decided to eat itself, there was a point in time that the voltage from the 12 volt side managed to make it through to the ESP8266. And the ESP8266 really doesn't like 12 volts, in which point it just yelled and gave up the ghost. So we need to make sure that we don't provide 12 volts to the ESP at all. So how are we going to do that? Well, we have got a new component in. Let's have a look at this component. So this, let's see if I can get this. In fact, so this is currently in, a cut tape. This has come from a reel. These components are on a reel and they get fed into an industrial pick and place machine, very similar to the Lumen PMP that I'm building. So what we're going to do, let's extract. If I got a pair of tweezers here somewhere, or if I've been tidying up the workshop today, so you'll notice the background is changing a little bit, and I am getting ready for a production run of a little side project which is challenging me to design and build and produce a 4-layer circuit board. It's quite a complicated board. Okay, we haven't got a pair of tweezers here, so I will need to find a pair before this is out, because I'm not going to try and hold components while we solder them. That's not going to happen. Right, so let's extract one of these voltage regulators and we'll get eyes on what it is. We'll call up the data sheet. I'll show you how to find the data sheet for the device. Right, so we only want one. And you can see we've got a lot of components here to experiment with. So that'll be good for future projects. And I think from here on in, anything requiring voltages above what can be provided by a LiPo cell, a single cell, then I'm probably going to switch over to this particular component and use it as my default. So let's go ahead back to the microscope. Let's get that focused in before we do. Let's get it centered. Alrighty, let's go. So here we are. Here it is. It's the AMS 1117-3.3. So whatever well, we're going to have a look at the data sheet, but the 3.3 bit of the data sheet is telling us that this is going to output 3.3 volts. So I'm going to open up a browser and we're going to bring that on screen in a second. We're going to search for this component. All right. So let's go to the scene. Oh, really? Really? Okay, give me one moment. We've lost my screen a moment. It seems to keep forgetting my screen. Come on, OBS, do your thing. All right. So we're going to search for the model number that is on the voltage regulator, and it is an AMS 1117-3.3. Okay, so let's grab the advanced monolithic Systems, that is the manufacturer of this component. That's where the AMS comes from. And this is a data sheet. This tells us the specification of the component, what it can do, what it can't do. Hey, see you, Waffles, welcome in. Hey, Buck Naked. Nice to see you there on Twitch. Appreciate you. So, what we're going to do here is we're going to scroll down. Now, we already know, right, from the first voltage regulator, it said it was like tolerant above 12 volts. So we're going to prove. You're here so you don't get fined. Lols. All for the lols. Right, so we're going to find out what the datasheet said, and then we're going to prove it. We're going to take a real-world example of it and see whether or not it is tolerant to that voltage. So let's have a look. So you get, like I say, different variants. This is the AMS, where are we? I'm just looking for mine. I'm looking for mine. There is mine. AMS 1117. So we know that the package, so that each package, what is a package? A package is the component shape and dimensions. There are set standards for certain components so that we know that it conforms to some guidelines. So this standard is a SOT or SOT 223 component. So that will be important later when we go to replace this in the schematics. We want to replace what we've got currently with a SOT 223 component, and then we have to wire it correctly. A quality approval denied, right? True that, Dimitri. True that. Okay, let's get this microscope out of my face because then I can see the screen. So it tells us what the component pins are. So pin 1 is ground, pin 2 is voltage out, and pin 3 is voltage in. So pins 1 and pins 3 is where our 12 volts are going to be coming in. And then pin 2 is where our 3.3 is going to be exiting the component. Right then. So let's scroll down a little bit further. Now we need to find out some specifications of the component itself. Specifically, what voltage can it take? So let's go down to our 3.3. So it's showing us that it's got 4.8 volts coming in. And then it gives us a minimum is 3.2. Typical is 3.3. Maximum is 3.399. So these are the voltages at 4.8 volts. This is what it's going to output. Okay, so we now got to find out what the input voltages are. So I'm just scrolling at the moment until I find the information that I'm looking for. I might do control find in a minute because there's a lot of technical data in this document. This is all like scientific sort of measurements of the performance of the device. And if you're like building a hypersensitive circuit or a really tightly constrained circuit for, I don't know, from some sort of regulatory sort of perspective, you need to have all of the, you need to understand that the component is going to operate to what you're expecting, yeah? From a hobbyist perspective, where I'm coming from, I just need to know I can put 12 volts into it and get 3.3 volts out of it. And there's enough current on it that it will supply my microcontroller and we won't have any sort of power brownout problems. So let's have a look. We want the input voltage range. In fact, that's what we're going to do. We're going to do a search. Control find. And we want input. Input to output. Input voltage. Okay. Absolute maximum ratings. Okay, well that's good to know, right? 12 volts in, 210 out. Seems legit, right? About us, welcome in. About us, and anybody who's lurking in Twitch, we are live streaming on both Twitch and YouTube, so don't get freaked out if I'm seen to be talking to myself. And equally, if you're watching on YouTube, if I'm talking to somebody who's not chatting, then the reason for that is because they're on Twitch. I will keep a separate window open so I can see my YouTube chat, because one of the streams that I did, one of the recent streams I did didn't have all of the chat going on, right? So I need to make sure that that's in place. Nice. All right. No, I'm not doing the import. I'm not doing the import of YouTube because there was a bit of crosstalk, and I know that there's like Twitch terms of service that you don't want to violate. Someone could say something really nasty on Twitch and get me into trouble on YouTube, and vice versa. So I'm keeping the chats isolated for now. I might set up a page where people can go and view the stream and see the chat all in one, right? I'll have a look into that. That might be something worth looking at, if that's technically possible. Okay. Caught up on chat. So thanks for everybody who's lurking. Appreciate you. If you're watching on YouTube, if you're liking what you're seeing, please give it a thumbs up. If you're not already subscribed, go ahead and hit that subscribe button. And if you're over on Twitch, hit that follow button. Remember, follows and subscribes on the respective platforms, Twitch and YouTube. Both of those activities are free, and it helps the channel a lot, so I appreciate that. Okay, so let's take a sneaky peeky look at the technical details of the AMS 1117. So the maximum input voltage is 15 volts. So we need to limit our project to 12 volt only, right? Maximum 12 volts. We would have to change the voltage regulator for a higher spec voltage regulator if we wanted to go to, say, for example, 24 volts or higher. So there we go. We have a ceiling for this project. Now we need to prove that this is correct. So let's have a look. Let's have a look at the abomination that has become of my board. And it is an abomination. Let's get the microscope. So we already know that the ESP is dead, right? It's gone. And we're now looking at the board. So what we've got here, let me just explain the anatomy of what is going on here. So right now we have 12 volts. I mean, in fact, let me get it. Oh, I've got to find a pointing thing. So we have 12 volts coming from this little pin just here, okay? And that goes off, and I cut the trace to this top pad here. And the reason I cut that trace is because that's the enable pin, and the data sheet for the first SOC23 voltage regulator says you tie the V in to enable. And I thought at first that this was the reason that we had the failure, was that the enable pin was a logic pin and should have had no more than 5 volts, and it received 12 volts and it died, right? It turns out that this little arrangement under this like ball of crud, what you can see here, this is actually solder mask. This is black solder mask, and essentially what I'm attempting to do here is I've got a resistor array, and there's 2 resistors in here that allows me to get 3.3 volts from this component. And if I bring you down close to that abomination, you can see these copper wires emanating from these 2 resistors. So the 2 resistors are here, and we have 12 volts coming in here, and we've got ground over here, right? So the ground wire you can just see coming through here to the center pin. In between the junction of these 2 resistors, what we'll have is our, I think it was 3 volts coming out. Right? Yes, not covered PCB. You ain't joking. Wait, earthquake cam. And essentially, these wires were intended to supply 12 volts to the voltage regulator. It was then intended to get ground to my resistor array, and then 3.3 volts over here, or 3 point something volts over here, to trigger the enable of the voltage regulator. And it turns out that even with us getting 3.3 volts measured here, it was still sufficient enough to flambe, as Woodcraft by Owen on Twitch says. Hey, Woodcraft by Owen, how you doing, buddy? Appreciate you. So we are recovering from a blown voltage regulator which decided to eat my ESP8266. The datasheet said it was 12 volt tolerant, and it appears that it wasn't. Hence, the magic smoke was released from this concoction. So we're switching out the voltage regulator for an AMS 1117 3.3 volts. So it's already had its voltage selected. We now need to clean this board up, and we need to get access to the pads, and we're going to essentially just trigger. I've just been triggered by my camera freezing, so I'll finish what I'm saying and I'll fix it. But yeah, we're essentially going to swap out with a beefier voltage regulator in the hopes that that's going to resolve the issue of being 12 volt tolerant. So my camera just froze out as I turned on my the power supply for my soldering iron station. So let me just pull my camera. There we go. Excellent. All right. So let's get the sponges damp. We're going to get to work on this PCB, and we're going to start opening it up, removing all of the bits that we've put in here in an attempt to work around the problem. And we're going to start from ground zero. By the end of this, we're actually going to validate that this AMS voltage regulator is going to work with 12 volts. One way or another. It's either that, or we're going to get more magic smoke. Magic smoke's always good viewing, right? So let me just quickly grab some soldering components, or desoldering components, as the case may be, because we're going to need a pick. I think that's all we're going to need right now. Cotton swabs, and we need the isopropyl alcohol because we're going to clean up the board. So, okay, I just want to be very clear with everybody. Let me just set the expectations of what we're about to do. This is not going to look pretty. This is not going to look polished, right? I don't want to detract from the quality of PCBX's circuit boards. Their circuit boards are pretty nice, right? I'm really pleased with the quality of the boards that I got from those guys. So, in fact, I should have really put a link to them in my description, but I forgot because I was like lastminute.com. Anyway, streamer life. Oh, I need a pair of tweezers as well, don't I? Because Steve, You're not going to grab hold of the boiling hot components now, are you? And the answer to that is probably. Okay, we've got a fine set of tweezers. Fine in the sense of the height that they come to. I do have a pair of tweezers that are currently AWOL, so we're going to need to dig those out. So I think the first thing I'm going to do is change the scene over to the microscope. Right, and we're going to get in here and we're going to remove these. We're going to remove these wires. Now these wires look like they, especially these ones, right? They look like they're crossing from like the 3.3 volts from the ground. It looks like we could be grounding those out, but this is a special kind of wire. It's called the enameled wire, and it's copper wire with an enamel coating, and it essentially is isolated. It's insulated electrically, and it can touch other wires and not be a major problem. So I'm going to rotate the board. I'm just going to set this up so I can work on it and hopefully give you a bit of a view of what's going on. So let's go ahead and get the ground wire out of there. And this should be low temperature solder. So I should be able to grab this wire and just yank it out of here, right? The iron's nice and warm. We'll come in and just touch this center pin, grab the wire with the tweezers, and there's the first air wire removed. Now, just to give you an indication of how big that is, there's my fingertip. It's tiny. How is life treating you, Owen? I hope all is well. Okay, that's wire number 2. And now we've got to get rid of wire number 3. And we're going to come in here and grab... Oh my word, is that rain? Can I hear rain through my headphones? That's crazy. Okay, the solder mask is covering that, so we're going to have to just pick away at that and just expose it. There it is. Okay, I'm hoping I'm like... This is like really awkward. I don't want to scrape away too much of the board because there are traces in here that we do need, especially for validating if this is going to work. So we want to validate the fix that we're trying to apply here. There we go. Excellent. Okay. All right, now we've got to get this abomination of a resistor array taken care of and off the board, right? So let's do that. It's in here somewhere. So we'll remove the air wires first, and through the process of heating everything up, we'll get everything off the board. Okay, that's one wire gone. Now the center wire. Okay, we lost the component there, and we can probably just grab it now. Mmm, toasty. Yum, yum. Okay. Now let's see what we've got here. I'm going to quickly bring up a schematic of the board because I need to know where I can and can't start scraping away at traces, because I don't want to damage anything beyond what's already damaged. Now, I could use another board, right? But what would be the point in that? Don't think it's this one. No, it's not. I've opened the wrong version of KiCAD. That'll be why. Ah, there we go. It's more familiar. Okay. Here we go. So let us take a look at the circuit board and where we're at, so we know what components, or how much we can scratch away. So here's the circuit board that we're working on. This is the design files for it. And if I come in here, we're in and around this area, right? So we've got a 12 volt coming in, and then it comes along here, comes to this via, and then goes to this enable pin, right? Now we've broken the trace here, so we can just clean up. We can just clean up north of this via here, and make sure that's all good, right? So let's come over to, let's get the geography of what we're looking at, right? So here is the first. Let me just bring this a little bit more on screen. There we go. Right. So here's the first via coming up, and that comes to the 12 volts. And we've lost a pad here, right? Because of all of the messing about we've done. So that goes down through the board and it comes back up here. And then we've broken the traces that takes this up to here. So we could probably just give this a little bit of a clean and call it a day, right? Because we don't really need to get in here at all. So the pins that we're interested in is this one, these two here, right? We've got our ground, which is this middle pin here, and then we've got our voltage out, which is this pin here. Now, the capacitor I spoke about earlier looks like flies on McDonald's, right? Tell me about it. So the capacitor is a little bit cooked, right? It's discolored. That was, in fact, it's cracked. So that's seen better days. Poor capacitor. So is the diode. The diode's been had seen better days. Oops. Mind you, I don't know if that's from 12 volts hitting it or me hitting it with the air gun. I don't know. One or the other. So we need to shoehorn this component to make it connect to the pins that we're interested in. So let's get a cotton swab and let's just clean this area up a little bit just so we can see what's going on. And then we're going to perform a little bit of surgery to make this voltage regulator do what we need it to. So like I say, this is my fault for not using the correct component in the first place. Or should I say the component not behaving as we thought it was designed. So let's bring our new component in so we can do a bit of a size comparison. So the old voltage regulator sat here, right? 12 volts, ground, enable, 3.3. Here's the new voltage regulator. And if nothing else, we know that this thing is going to handle more current than its predecessor. So I need to come back to the data sheet to find out what the pins are again, because I've forgotten. So if I scroll up, right, so pin 1 is ground, pin 2 is voltage out, and pin 3 is voltage in. Okay, so that means I need this pin to pick up a ground from here, and I need this pin to pick up voltage from here, and then I need this pin to give me 3.3 volts there. So we need to now figure out how more equals bigger smoke. Probably right, Road Rally Race. Probably right. So what I'm thinking is that we look to possibly shoehorn it here. So if I can pick up, see if I try to pick up voltage there. So, come on. So that's my 12 volt line. And this is my ground. What are we thinking? I'm wondering if I can use this fiducial. Can I put some solder on this fiducial and mount the component like here? And then we run some trace wires. See, if I do that, that's going to give me 3.3 volts short to ground. So I need to be incredibly careful. Now I tell you what we could do. I just thought we could possibly bend the pin upwards. So that'll give us a fixing point, right? Might actually be worth finding out whether this tab at the top is connected to one of these pins. That would be very useful to know, because then I could possibly mount it like something like that. If it's, oh yeah, there's a couple of options here. But ideally I want to try and get this onto a pad so that it's got some sort of mechanical bond to the board and it's just not floating in midair. So let's break out the multimeter and we're going to figure out if that big broad pin at the very top, does that connect to anything down below, and can we leverage that to our advantage? Now this could be an electronics repair job where, you know, you need to replace a blown component and you don't have a replacement part, and you're kind of fudging it to try and get the component to work. Okay, let's get some light on here because my hand is definitely going to block the light. Okay, so what do we got? Come on, camera. Earthquake cam. Right. So put our probe. Let's just yeet the component across the screen, right? Okay, let's pin 1. No. Pin 2. Yes. Pin 3. Okay, so that is connected to that at the top. Okay, let's show it again. I don't know if you guys are hearing the beep. Can you hear the beep? Don't know if you can, but okay. So that should be 3.3 volts as well as this in the middle, right? So we got to be super duper careful right now as to how we mount this. I think what I might do, can I spin this around and that's not going to work. I may just have to go with soldering to this via just here, this via just here, and then do an air wire from here to ground, and then an air wire here to 3.3 volts here. I think that's likely what I'm going to need to do. I just need to make sure that this is not going to short out on something. This via is not connected to anything. It's just a blank pad. Yeah. So we can sit on top of that and not really have that much to worry about. So let's grab the solder. We'll put some solder on this voltage pad here. Just get this component out of the way for a moment while we prepare everything. Okay. So we're using a tin solder already. There's a flux core. So it's a flux solder, sorry. We've got a nice blob of solder there. And that should be connected from this point here to this point here. And it is. Good, good, good. Okay, so we're about to make our first connection for voltage in. Let's get this show on the road, shall we? Let's get this component installed. We need to rotate it so that it's not touching anything else that it shouldn't be. Okay. That's reasonably stable. I'll tell you what I am going to do. I'm going to put some solder onto this fiducial. I'm going to flood this pin here. Like that. There's plenty of solder for us to work with now, right? But it's now it should have a more thorough connection. So, but the only thing I'm noticing right now is we are incredibly close to J1's pin here. So this is 3.3. If that's ground, that's a problem. That's a problem. So let's have a look at our diagram for J1. What is going on with J1? Okay, so that is channel A. So that is a switched ground, which theoretically shouldn't be a problem because we're not necessarily going to power this MOSFET. We're not necessarily going to put the ESP12 in place. But I think what we're going to do, just for safety's sake, I need to grab some Captain tape. Captain. And I'm going to place some Captain tape underneath that pad. I'm going to raise the component up and I'm going to drop some Captain tape there. All right, so Captain tape is a high temperature insulation tape. You often find it on 3D printers wrapping the electronics around the hot end. Okay, I want to be clear to everybody. This is a bodge, right? This is not how this circuit is intended to operate. This is not normal service. I'm trying to get underneath the component to lift it. You watch, I'll end up either spiking my hand because I'll slip. I really don't like prying on things like that. I think we're going to have to heat it up. But Bro Rally Race, you're probably right. It's probably going to be more smoke because the component is bigger. You never know, right? Oh, as he punches the microscope. Would help if I switched the scene. Let's bring you guys up a little bit. I've just pulled my microscope off its mount. That's not ideal, is it now, Steve? You do have to get a better mount for your camera, or your microscope camera, because everyone's going to get seasick before too long. All right. Okay, so switch one is... Where is switch one? But yeah, so you got to... There we go. That's where we're at. It's a little bit better. Right, so we need to warm this up, and we need to get this component off that pad. As Serge would say, we gave it a little twist. A little lemon twist. Name the movie. Name the movie. All right. Let's just quickly make sure we haven't done... Let's just make sure we don't have any shorts in the places that we don't want them. I need a ground pin. Okay, ground, Steve, that's not connected. There we go. Perfect. Silent mode, bang on. Bang on. You got it in one. Beverly Hills Cop. Okay, we don't need the Captain tape anymore because we managed to bring that component off. Right? So what we do need to do now is to use some enameled wire. And I've got... This stuff is pretty thick. And unfortunately for me, it doesn't easily... Let me bring this up here. It doesn't easily clear off. What normally happens is you use the heat of the soldering iron to burn away the enameled coating, but this stuff needs to be scraped. Hey, Silent Mode, how you doing? Welcome in. Thank you for checking out the stream. So we're live streaming on Twitch and YouTube simultaneously. And we are recovering from a little bit of a boo-boo that I made. I had the... I'm going to tin this wire now. Tinning is the process of putting solder on the end of a wire to prepare it for soldering. It makes the soldering process a little bit easier. Well, it would if the wire would behave and not like want to... It's camera shy. It doesn't want to be on camera. I'm doing very well, thank you, Silent Mode. Appreciate you asking. What we're going to do is we're just going to get some fresh solder on this iron. And we want to visually see the solder on the wire. I don't know if you could see that. See if I can get a better shot of what's going on. So can you see that the wire is now gone silver? There is solder on the end of that wire. And what we can now do is we can take the wire and we can connect it to that central pin. Oh my word. I so need to get a better setup. I need a better bench. This microscope camera is like Seasick Town. Seasick Steve. Right, let's get the tweezers. Let's get the tweezers so we can control the wire a little bit more finely. Okay, now we're just going to bring the iron in. We're just going to heat this, let it melt the solder. And that is not connected. Not yet. It will be in a second. Heat is being drawn away at the moment. There's a heat soak going on. Oh man, seriously? All right. Not playing ball. So I'm going to put a little bit of flux on here. You know, flux is it enables the solder to flow. You don't need too much. That's probably a bit too much, but we'll live with it. Okay, I'm going to rotate this because this is a little bit awkward for me. There goes the wire. The wire's just yeeted itself. All right, where are we? There's the jog. There's the landscape of it all. I should really put it like this. Where are you? Where are you? Lost in space. Danger, Will Robinson. Okay, you'll watch when we heat this up. The flux will just melt away. Okay, and there's our voltage out. Buzz Mixer, thank you so much for the subscription on YouTube. Appreciate you. Thank you. All right. We're going to bring this wire. Well, that wasn't fit for purpose, was it? This is why I don't like this enameled wire. It is being a pain. This enameled wire is an absolutely pain in the bum. Okay, that's better. Now we're talking. Okay, so that has got to come all the way over here to this pad by there. So let's get the tweezers and see if we can form a little bit of a trace. So this is actually good practice for trace repair. So I want it to come away from that center pin. Because that center pin, oh, dang it. Why will this not take? Right, I'm just going to prepare this wire off screen, but for some reason this darn enameled wire is not affixing itself properly to the pad, and the only thing that I can think of is that there is still enamel on the copper, which is interfering with the connection that we're trying to make. Oh, okay, silent mode. You're making a photo turntable. Is that just a mechanical, or is there electronics involved in that? And if so, how are you achieving the rotation? Right, here we go. So we got flux in here. We should just be able to come in and sweat the connection, right? We should just be able to melt. Okay, I just want to make sure that that is a good connection, and it's not shorting over to the other pin. Right, that is a good connection now. Thank goodness. That was really starting to mess with my head, right? Ah, there would be a Pico and a stepper motor involved. What stepper motor are you going to use for that project? Is that going to be a NEMA 17? Is it going to be something smaller? Is it going to be a pancake drive? What are you using? Or have you yet to decide? Okay, so we're avoiding this. Well, we're avoiding a few things here, right? So I think what I need to do is to bring this trace around. It doesn't matter if it touches, because the enamel creates an insulation. There we go. And I'm trying to get some space here for the ground wire. Ah, okay. Well, you know, there's lots of options out there from stepper motor point of view. So a Pico and probably something the likes of the Pololu stepper driver. Right, I'm just going to flip the board round in the vise so that I can get a little better access to hold and clean up these things. So I'm a hobbyist. I'm not an expert. I've never really done this as a paid job. I know there are others on YouTube that they do this for, or have done this for, a living. So they would, if any of those guys were in like Tronics Fix or Joey Does Tech, or you know, there's a myriad of guys who do really good work on YouTube for PCB repair and stuff like that. If they saw this, they would be like, oh my God, what are you doing? Well, I'll tell you what I'm doing. I'm learning. And I'm learning in front of everybody, because I think it's really important to document that the learning process is where it's at. I like to show, because a lot of the videos that you see on YouTube, they're produced and you only get to see the take that was successful. You don't necessarily see the 17 different takes that failed. And I like, with my live streaming, I definitely like to show the failures, which is why we're dealing with this problem. Okay, so that should hopefully be a good connection onto this pad. And it is not. Okay. So let's see. Ideally, I need better enameled wire, if I'm brutally honest about it. But we work with what we got, and we make it work. Okay, that's on there now. So the next thing I need to do, before we go any further, it's always good that you check your work as you go. Right? So we know that our voltage regulator has got 12 volts. It's going to have 12 volts coming in, and it's got 3.3 volts going out. And this wire needs to go to this middle pin here for the ground. But we see that this is running across this pin. We got to make sure that it's not, that it isn't shorting out on anything. So what we're going to do is just quickly measure that we've got voltages where we should have them. Perfect. Perfect. So the only thing I need to do now is hook up a ground wire from here to this pad. So let's get that done. And then we're in a position that we can test that the data sheet for this particular component hasn't lied to us. We would not be in this position had the data sheet for the component supplied was correct, or that the component was manufactured to the specifications of said data sheet. You know, it's really sad that we're here, but I guess that's life, and we have to work around it. We have to work around that problem. Right, so I'm going to use this bit of enameled wire now. I'm going to prep it. I'm not going to do this on like close up because one, you don't want to see earthquake cam. And two, it's a bit of a pain to show it properly. So all I'm using is a scalpel to scrape away at the enamel coating. So silent mode, what are you going to use your turntable for? I know you said it's a photography turntable. What is your subject? I think I know the answer, but let's not assume, shall we? Makes for good conversations. And you know what they say about assuming. It makes an ass out of you and me. Okay. So let's see if we can't get this hooked up with a ground wire now. Okay, so is that going to be like a stop motion? Is that going to be like a slow-mo? Is it real time? If you guys aren't following Silent Mode on YouTube, Silent Mode is a Lego fabricator. Give him a bit of love on the YouTubes and give him a subscribe. Subscribing on YouTube is for free. And it really does help the algorithm. Okay, so now we've got to guide this wire over. You're very welcome, sir. You are very welcome. So let us kind of nudge this into place. Again, this doesn't have to look particularly pretty. It just has to be functional. All we're doing is we are validating that this voltage regulator is going to be 12 volt tolerant. And will perform its function before we update the CAD models. Okay, we've got to do a bit of scrapey now. Buck Naked, thank you for giving Silent Mode a shout out on Twitch. Appreciate you, buddy. So what I really love about live streaming is the people that I meet along the way. The maker community, regardless if it's on Twitch or if it's on YouTube, is amazing. And it's all about helping each other, right? It's all about promoting what each of us does. Okay, I think that's going to be enough. I know I haven't got the enamel on the backside, so I just hope I can pull this next pad soldering bit off. This is going to be a bit of a it's probably a bit much flux, but me. Yeah, thank you, Buck. Appreciate that. Okay, so what we're going to do is we're going to come in here. We're going to melt the flux so we can see what's going on underneath. Okay, so now we want a nice bit of solder on here, but we don't want too much that we bridge. I need new soldering tips for the look of it, because the solder doesn't want to go where I want it to on the tip, which is close to the work. You can see the solder balling up on the back of the iron. All right, so I think we'll test that with a pair of tweezers now to make sure that that connection is solid. And then we're going to check our work. Oh, look at that. I thought that was soldered and it's not. What an absolute tease. So what we're going to do, I think there's sufficient solder on the pad and on the wire. I think we just need to bring these two together. That is one thing that I find with a microscope, a video microscope, is that you lose depth perception. So trying to get things where they need to be in relationship to one another can be a little bit of a challenge. Okay, that is now solid on there, but my fear is that there's a short here somewhere. So let us, yeah, it could very well be enamel underneath. I was hoping that the heat from the solder would cause that to peel up. So what we're going to do is just make sure that I get ground. Okay, I got beeps. I don't know if you guys are making out the sounds, but we do not have awesome. So that's ground. I need to find a ground plane. Perfect. So that's connected. Okay. So I think we're in a position to be able to test, and hopefully we don't see this, right? This is what we're fixing. So for those of you who joined late and not quite sure what's going on, we did a project where we put a voltage regulator in. Its voltage regulator was supposed to be 12 volt tolerant, and when we put 12 volts into it, it did that. We said the magic words and the magic smoke was released, right? So that's not what we want. So let us just quickly test everything, right? First and foremost, I want to test between ground and 12 volts. Make sure we don't have a 12 volt short, which we do not. Yes, Buck. Is there... Okay, my YouTube chat seems to be lagging. One moment, please, guys. Thanks for the heads up. The last I see is silent mode asking if there's enamel underneath. Which we answered that one. Are you seeing more? Yeah. No, thanks, Buck. No, I appreciate it, because when YouTube chat went on the fritz for me, one of the streams, people were chatting in YouTube, and I wasn't responding at all because I couldn't see them chatting. So I think I fixed that. So main part of the stream is coming, says Road Rally Race. That's okay. All good. All good. Right. So we've got no short on the 12 volts, which is good. Let's just make sure we got no short on the 3.3 volt line. Okay, we don't have a... Side cam is frozen. Oh, yeah. Why? What a predicament. Why is it... Why? Oh, I see what's happened. I see what's happened. My camera has become disconnected from power, and the battery's just gone flat. One moment, please. Let me remove the camera. One moment. And you guys are upside down. You shouldn't be seeing that. Let's flip you over. Here we go. That's more like it. You do it! What's happening, buddy? What are we doing? You do it. You came in at a brilliant time, right? We're about to fry stuff. We're about to have that very acrid electronics smell, potentially, right? So I built this low voltage controller, right? It's a 4-channel low voltage controller. It integrates with HomeAssistant via TAS motor. The TAS motor firmware gets loaded onto here. HomeAssistant picks it up. We can configure it to control up to 4 12-volt channels or low voltage channels. When we tried this on a Twitch stream, we powered it up, and this happened. In slow motion, you'll see the magic smoke is released. And just for good measure, let's see that in close-up, shall we? Close-up and slow motion. We say the magic words, abracadabra, and the magic smoke was released. The data sheet for that voltage regulator said it was good up to 16 volts plus. Either that component does not comply with the data sheet, or the data sheet was lying. One of those statements is true. So we've upgraded the voltage regulator, and we've just done some transplant surgery to integrate a AMS 1117 3.3 voltage regulator. It's the type of voltage regulator that you see on the big boy Arduino projects. I'll give you an example of what I mean when I say big boy projects, in that this is the SOT23 type footprint that the original voltage regulator sat on, and here is our new voltage regulator. All right, so this one also says that it is good for up to 16 volts. Unfortunately, we managed to kill our ESP8266. So what we're doing here is validating that this voltage regulator is going to be sufficient to handle the 12 volt input and provide us with a good 3.3 volts before we update the circuit. Now, the thing is, right, I got these circuit boards from... What a big regulator you have. All the better to power your circuits with. Why? The thing for me, right, is that I got these circuit boards from PCBX. PCBX supported a previous stream, and they provided me these circuit boards, right? And they're pretty nice. I gotta be fair. If you're watching the replay of this, there will be a link to PCBX in the description. But yeah, these are really, really nice circuit boards. And we would not be in this position had it not been for the fact that the voltage regulator is not rated for 12 volts, even though the datasheet said it was. We would be further down the road of automating my lights, cleaning up my power, which is what the project's all about, had that voltage regulator not decided to do a RUD on stream. That was kind of but it's a learning opportunity, and we are, as I say, we're transplanting this in. This is ugly as hell, right? So we've got the ground, we've got the 12 volts in tagged to a via. We've got our voltage out going to the original voltage out pin. And we have the ground wire brought in on these enameled wires. And like I say, this is not pretty. This is Frankenstein. This was supposed to look super clean. If you saw the Twitch live stream, you will have seen that I used my reflow oven. I've managed to build a reflow oven, and we used solder paste and everything, right? We stenciled it, we soldered it, it looks so clean. And then the regulator decides to go, Yahtzee! So, yeah, when life gives you lemons, you've got to make lemonade. And here we are, learning how to do, technically what we're doing here is trace repair. And we are transplanting in this AMS 1117 in order to see if it is going to stand up. Before we put this anywhere near a new circuit, we're gonna give this a run for its money on just the regular sort of voltage without a chip on it. All right, can this handle it? So we've got no shorts on ground to 12 volts. We've got no shorts from 12 volts to 3.3, so we don't have any leakage of higher voltages. I'm not going to say high voltage because it's not. It's all low voltage. 12 volts considered low voltage. So yeah, we got no leakage of 12 volts onto the 3.3 volt rail, and we don't have a short from 3.3 to ground. So that is, we're in good shape, and all of the pins of the voltage regulator buzz out to the destinations that they should. So electrically this is connected, but it just looks really janky, right? But we're going to fix that. We will fix that, I promise. Right, let's get the side camera back up and running, because that decided to give up the ghost because it got disconnected from the battery supply. So the device is just starting up, and we'll get our side cam all back up and running. Look at that. Look at that. In that moment, we probably killed the LED, we killed the voltage regulator, and we killed the ESP8266, because probably what happened was some amount of voltage above 3.3, probably 12 volts, made it to the ESP8266. And it said, ouch, never to live again. So we might actually get the, we might do a dissection. Depending on how quickly we get this tested, we might dissect the ESP8266 and delid it and have a look under the hood of the microcontroller and see what's underneath it. But let's see. Now, I will warn you guys, if I disappear off stream when I plug this in, what's probably happened is I've tripped the electrics in my home because I've shorted something out. Here in the UK, we have pretty good safety measures. That's not to say that you should be complacent with mains voltage or anything like that. But yeah, anything like that, we're likely to see the mains electric trip. So if the stream ends abruptly, either just before I plug in the power socket, all my electrics in my house are now off, and I'm strolling around in the dark because it's after sunset here. Let us power up my camera. So we should now be getting video from my side cam. Let's go to the side cam view and switch it on. Hello! 2 thumbs fresh. Yes, let's do a poll. Buck Naked on Twitch says, shall we do a poll? The question is, do we think this is going to work, or do we think we're going to release some magic smoke? In fact, hit one for it working, 2 for releasing magic smoke, or 3 for blowing the electrics in my entire home. What is it going to be? 1, 2, or 3? Place your bets now. While we're doing that, I'm going to prepare. I'm going to prepare. One, it's going to work from silent mode. One from Buck Naked over on Twitch. We've got 2 votes in. I should really find a way to do some sort of poll that can work across both platforms. That would be kind of cool. Okay. Oh, I'm nervous. Any more votes? Place your bets. We'll give it another 30 seconds, and then we're gonna get to it. Early stream night. Does that mean if you think it's gonna be either 2 or 3? Also, tell me, do you want the overhead cam or do you want the side cam? Which one you want? We can do this one, or we can do this one. In fact, we can do this one, and we can do this. Ha 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 ha. I'll probably go a little bit more before it starts to like pixelate bad. Okay. Side enhance, right? Ooh, there it is. There it is. Okay, so we're gonna lose this light, right? Because I gotta pull the power out of it. Because it's the power supply. That's what happens when you pull the power supply, it goes off. Okay, we're getting dark here now. But you can still see me, kinda. Okay, let's just pull back a little bit. push forward, and you can see me plug it in. This is the magic smoke. I'm not actually gonna be watching this for real. I'm gonna be watching this on my computer screen to see what happens. Okay, so if it's number one, this is gonna be very anticlimactic. Nothing is gonna happen, right? Visually. And then it's a case of testing out the various points to see whether or not we got voltages where we should have them. If it's number two, you're going to see the magic smoke release itself. If you're on Twitch, get ready to clip, okay? Because this is going to be clip-worthy, right? If it's number three and all my electricity in my home gets tripped, then the stream, you probably won't even see it, right? Because there's approximately a 20 to 30 second delay on the stream. So, you know, I'm potentially not going to see it. Yeah, right, silent mode, fingers crossed. Okay. Here we go. Here goes nothing. In 3. And we don't know the state of this capacitor. Ooh. Ooh. Wait. Hold up. Hold on there. Let me just quickly... It should be fine. It might be open circuit. But I just want to make sure this capacitor isn't shorted to ground. It shouldn't be. It shouldn't be. Okay, we got no beeps. We got no beeps. Okay. Here we go. Here we go. In 3. In 3, 2, 1. Okay. The music stopped in my ears in that moment. I can see it's still... Okay, now it's stopped for you guys. Oh my word. Okay, we don't see any smoke. We don't see any smoke. Okay, this is a good sign. Still looking good, still online. Okay. I just knocked everything on the floor here. I'm getting a little bit hysterical. Anyway. Okay, so let's check with the overhead camera what our voltages are. If our voltages are good, right? If our voltages are good, we are good to make updates. So you can see the voltage meter. We should have 12 volts on this line. And we do. Right, we got 12.2 volts on this line. The question is how many volts do we have on this pad just here? If we've got 3.3 volts on this pad here, winner, chicken dinner. Okay. Was that smoke or have you started vaping? No, I can't. You're making me try. You're trying to second guess me here. Road rally race. You're trying to make me second guess things. Right, here we go. Here is the 3.3 rail. Here we go. What do we get? Our survey says 3.36. Winner. Chicken dinner. Gets him. Ah. Oh no! So the guys over on Twitch have just had an ad roll. So they need to let me know when they're back. Let me just send them a message. There we go. All right. It didn't blow up. No, we're still here. We're still here. And if I put my ground wire here and my pin on VCC for the ESP8266, we get 3.36. Oh, still ads on Twitch. What do you mean, dang it? You do it? Ad break is done. What are you doing? What do you mean? Were you hoping for the magic smoke? Were you hoping for the fireworks? Were you hoping for the stream to suddenly cease to exist? Now we're back. So, for those of you on Twitch that just saw an ad break, if I just come in here with the meter and just tap on the VCC pin, we get 3.3 volts. Now you do it, just said dang it out of context, and I'm trying to figure out what he means. But no, that worked. So even though this looks like a Frankenstein mess, it works. So what does that mean for us? Well, it means that we can now go ahead and update the design of the file with a new voltage regulator that will essentially not do that. We don't want that. So let's wrap up what we need to do with the CAD files. Let's get the light back on. God, all of this to try and automate some lights. And some people say it's easier to like buy stuff. And they're probably right. They're probably right that it is easier to buy stuff. But where would the fun be in buying everything? Learn how to make stuff, and then you can just make, you get an education as well as the thing that you want. That's predominantly the reason I do this. Okay, so let's go into KiCAD and let's bring up the schematic editor because we got to do an update on the schematic. Okay, so here is the schematic for our circuit, and this is the component that we use, the SPX 3819M5-L-3-3. This is the voltage regulator that should have been 3.3 volt compliant, 12 volt compliant, or greater than 12 volt compliant, and it's not. So what we're going to do is we're going to place a new component, and we're going to search for the component in KiCAD. And we can search by the part name. So hopefully we have the library for it. So AMS 1 There we go. AMS, they actually got the good stuff, right? And it's also got the footprint. So we got the footprint, we got the symbol, all in KiCAD out of the box. What's the max current on 3.3 volts? That's a good question, but it's going to be less than 500 milliamps. It's only an ESP82 8266. So yeah, it's not going to be particularly much. So, and I've successfully used the SPX voltage regulator in circuits which use a single cell, either an 18650 or a LiPo cell running between, well, just nominal 4.2, isn't it? So 4.2 down to 3.8. And it's worked absolutely fine for ESP32s, ESP8266s. It's absolutely fine. I just think that that is not it's not the right component for a 12-volt circuit, regardless of what the datasheet has to say about it. So let's delete that component completely. We can delete these markers here. $500 milliamp on a linear regulator is going to dissipate 4.35 watts. Yeah, I will say that the voltage regulator also, I went through about 3 or 4 voltage regulators trying to figure out what was going on. I initially thought the problem was to do with the logic pin enable not being tolerant to 12 volts. And the circuit diagrams that we use typically state that you just link enable to voltage in, and that should be enough to bring the voltage regulator online. Now, that being said, I removed the ESP8266 so that the circuit, the 3.3 volt rail, was open. It had no load on it whatsoever. And the voltage regulator still let go with a vengeance. So even with an open circuit drawing 0 current, it still ate itself at 12 volts. So that tells me that internally it cannot manage to deal with a 12 volt circuit, 12 volt input. So the data sheet was either incorrect or, you know, it lied. Right, let's get rid of that. So we've dropped this in place. I know that this is connected to my wires because the little boxes that show the termination, they're gone. And now let's just draw a line between here and here. This is a bus wire, standard wire. Okay, so now all I need to do is just check my footprint libraries. Run footprint assignment tool. So U3 could have components. But yeah, on a 12 volt to 3.3 linear, it's going to pull 4 watts. Yeah, maybe that was my naivety that the data set, I didn't read too much into the data sheet. I just looked at the maximum voltage that the voltage regulator could take on its input. I should have potentially looked at the table that says, you know, voltage in, voltage out, current dissipation, heat, all of that sort of good stuff, right? There's, like I said at the beginning of the stream, the technical data that is available in these data sheets, right? There's like a lot, right? And for people who are certified in electronics, you know, it's going to mean a lot to them, especially, you know, when designing circuits. But I'm a hobbyist. I'm a hack it and find out. If it blows up, then I learn something. I'm a kinesthetic. I'm a kinesthetic learner. I learn by doing. I don't really learn by reading and things like that. So yeah, that's the voltage regulator. Let's bring in the footprint assignment tool. Okay, and we'll drag this down. We're going to update the footprint names in a minute. You approve of blowing things up, says Zap Rebel on Twitch. Yeah, it's always good, right? It's you see physics in action, right? That's pretty cool. So there is our AMS 1117-3.3, and it's a SOT 223. That's the footprint that it's used. So that's right. If I now right-click this and view selected footprint, I get to see the footprint for real. In you know, this is what it looks like. And if I go into here, we'll see if it's got here we go. It's even got a 3D model. right? So we can actually bring this into our design. And we're going to need to get new boards made with using this voltage regulator. So as I say, I've successfully used that voltage regulator with single cell applications, and I will continue to do so. But anything that needs anything more than 5 volts, I'm going to be using one of these. And as I say, I've got them now on, I've got them in a cut tape. So these potentially can be loaded up into my Lumen PNP pick and place machine when that's up and running. And we can start running some jobs with it. So right now we need to finish off correcting our mistake. And you'll notice from, if you're watching on YouTube, I'm very open that this is my mistake. This is not PCBX's fault, because PCBX's circuit boards are pretty dang clean. I do like them. Yeah, this is a mistake on my part. So we'll click here. Let's bring up our schematic again. And I'm going to rerun the footprints. And we're going to reset all of the annotations. Okay, so we're going to annotate. And there we go. We close. So that just means that the naming conventions of all the components has just changed from what it originally was. Which is fine. But I didn't want it to be calling out U3 and U2 is not on the board. So anyway, we'll hit save. And now we need to jump over to our schematic editor. And you'll see that we've still got our SPX. So we'll grab that. Okay. In fact, we're going to delete this. We've got it selected. We're going to delete it. And we still got the footprint and the pads. We're going to have to fix all of this. We're going to do this. We're going to press this button here, right? This updates the PCB with the changes from the schematic. So it's just going to synchronize. It's going to synchronize everything up. Mistakes happen. Like that time you were going to charge a Tesla semi. It was just one time. I mean, come on. You give a guy a break. All right, we're going to hit update PCB. Okay, so we've actually got some updates in here that we didn't anticipate. So let's pop that up there. Oh, did I delete too much? I think I might have done. All right, let's quickly just do an update in place, in situ. No, it's thrown things around the blinking screen. Well, that's just rubbish. That's really messed with my melon, man. Move. Right. Delete. Goodbye. You are the weakest link. Update. PCB. Close. Okay, stick you by there. I'm going to move you, stick you by there. We're going to have to fix this now. All right, grab you, put that there. Let's get our ESP back in its correct position. Because it's all wonky donkey right now. Okay, so all of the wires, all of the traces. And now, oh, dang it, would you believe it? Okay, well, let's... When life makes you, well, gives you lemons. Okay, we're going to delete all the traces. Oh. Would you Adam and Eve it? This is turning out to be quite the problem. Okay. So how do I turn off this component? Okay, I'm just going to turn off a bunch of things until my ESP8266 goes away. Keep turning them off. Just keep going. Okay, now hopefully I can select my traces, and then we're gonna have to reboot things. It's horrible. Okay, get rid of you. All right, so we're just gonna remove all of the traces that connect to. See, I knew there was one in there. I knew there was one in there. It was hiding. I'm a pro in KiCAD. I never said I was a pro. I said I use KiCAD. But never did I say I was a pro. I wouldn't do that. I would like to think that I'm proficient, but pro? Not so much. Okay, so we're just deleting wires, traces that will cause us problems, right? So the component is not exactly in the same location as it once was. It's slightly shifted. Now I could delete, move the component, but I mean, being honest, it's probably easier. Just these traces need to be redone anyway. So I may as well get these traces updated and fixed, right? So let's get rid of that. Okay, so we now have a bunch of these blue wires, right? These blue wires are what are called air wires. So you do it says, well, you're definitely an expert. If you used it more than 5 minutes in our company, you immediately became the resident expert. I hear you, man. I hear you loud and clear. So we're creating all of these disconnects, all of these air wires, right? We're going to have to fix these air wires. IMC. I'm gonna abbreviate you. IMC. We are currently looking at an abomination. So we're recovering from an ESP 8266 failure. A failure in the sense that the your own abbreviation. I would mispronounce that name so bad, right? So yeah, we're currently recovering from a failure of a voltage regulator. The voltage regulator decided to eat itself, and in the process, deliver 12 volts to a 3.3 tolerant device. So what we're currently doing is we're swapping out the footprints for said device. In fact, do you know what I'm gonna do? I'm gonna do a global deletion. I'm going to delete traces and vias. Gone. Gone. It's gone. It's done. We're gonna do it all again from scratch. Screw it. Screw it. Let's do it. All right, I'm just going to turn all of my layers back on. Yes, I do. So I had these boards manufactured by PCBX. Let me go to the side camera. You can show this off a little bit better on the side cam. Zoomy. Right, so I had these boards made by PCBX, and to be fair, they are pretty nice boards. I did test it a little bit by making my screen printing incredibly small. Oh, I missed that event. I heard it, but didn't see it. So that must have been a sub on Twitch. Thank you so much for the sub, whoever that was. So yeah, this board is like, it's really nice. I like it. I like it a lot. This is the abomination that we have been. Oh, it's you just following. Awesome. Thank you so much. So yeah, this is the abomination that is. I can see why that happened. There we go. My effects were beneath my camera. So yeah, we've kind of Frankensteined the new voltage regulator on, and we've just validated that that's working. So what we're now doing is updating the CAD files so that it reflects what the device is doing. So I now need to move this channel A. So I think I now know what has happened. I have made the mother of all mistakes. So what has happened is that I've chosen to rename all of the components. So all of the J components have now just decided to go, oh, I don't exist in this diagram anymore. So yeah, that's why that's just done. That's why it's just pooped itself. Okay, so let's select my MOSFETs. Okay, and we're going to move them. I'm going to move them down to here. I'm going to move the fiducial. I'm going to get that off the board a moment. And then we're going to grab our voltage regulator. We're going to rotate it. We're going to see if we can sneak it. Oh, well, wouldn't you just know it, right? It won't go there. Will it go sideways? Oh, it'll just go there. Look at that. Okay, we can work that. We can work that. Move the naming convention there. It'll be under... Put that there. Oop. I need to select that silkscreen reference. I'm going to move it to there. Boop. All right, let's bring the fiducial back in. See if we can find a place to put the fiducial. I need 3 fiducials on this because the intention is that this is going to be built on my Lumen PMP that I'm building. So we need a minimum of 3 fiducials on the board. I tell you what I could probably do. I could probably rotate this capacitor. If I move it and place it there, like so, we can then take the fiducial and we'll pop the fiducial by there. Ta-da! And I'm going to remove the naming of the fiducial so I don't have to worry about silkscreen. And let's remove the namings on the other fiducials. That one's already gone. Okay, so let's quickly take a look at what this board will look like when we manufacture it in the 3D viewer. There we go. That's a little bit nicer, isn't it? That's a little bit smart, don't you think? I think so. Sweet. Okay. So it is time for us to do the routing of the traces. So let's close that. And let's just do a DRC check because I want to clear the fill areas. In fact, I'll delete this fill area a moment. And we'll bring that back in a minute. Right, so we're gonna just hit save on this for now. And then we're gonna use the auto router plugin. So the auto router is called free router. That's just initiating, and we'll cancel that and we'll bring that on screen so you guys can see it, because I'm good like that. Okay, so here's our layout, and we can now just say start auto router, and it's going to route my traces. What is the end goal of the project, says IMC on Twitch. So I have a set of lights that I use with HomeAssistant. I've got a circuit board that is installed in my main light, and it uses a series of relays to trigger high voltage, mains voltage sockets to turn my lights on and off. For example, Ziggy, turn streaming lights off. Yes, you can. Ziggy, turn streaming lights off. Do as you're told, device. There we go. Right. So that works. Ziggy, turn streaming lights on. So this is a combination of Node-RED, HomeAssistant, to kind of like gel all of these things together. So there's a couple of things wrong with my light, one of which is the current design means that if I have a failure of the primary server, I lose the ability to control my lights, and I need to retain local control of the devices. So I will be migrating the project from its current firmware over to Tasmotor. Tasmotor, if you Google Tasmotor, you'll find it is a firmware that you can install on a number of different microcontrollers that you can then control the GPIO pins of the microcontroller, and HomeAssistant just sees it. You can put things like a temperature sensor on it. You can put WS2812 NeoPixel LEDs on it. There's a bunch of things that you can do. So we've converted this into a 4-channel. We have built a 4-channel controller. So this has the ability to control 4 MOSFETs. Now, what I will be doing is I'll be making, right, here is a battery for one of my lights. This is the battery for my light. And I'm going to make a fake battery. Here is an analog of that fake battery. And this module is going to be installed inside like that. So this will sit on the back of the light module. 12 volts will come in through this power jack. And then there'll be a fly lead from one of the output channels that will go into the power of the light. So the 12 volt supply will always have this module running, and then I can like tidy up my lights. But the cabling, because if I give you a sneak behind the cloak, right? So there are the mains controlled sockets, right? The cables train across here to a box that is installed behind this light. And as you can see, I've got cables hanging from the ceiling. And these essentially are a bit of a hazard. I mean, it was great when I originally did the project. Good learning exercise. But there is a better way of doing it. And the better way is to have these boards do the heavy lifting. So that's what we're going to do. Now, in theory, what I could do, I suppose I could do some air wires off the pads of the original and have the voltage regulator floating in space, or I don't know, glue it somewhere on the board under some Captain tape. That would really be a fudge. So ideally, I want this to be resolved. So let's take a look at what the auto router has done. So here's the work of the auto router. And let's have a look at what we've got. So we've got large thickness traces for our voltages, which is good for our grounds. Our 12-volt line here for channel A is coming out here, and that's good. But you'll see you've got this really tiny sort of piddly little trace for the 12 volts, right? So we're going to fix that. We're going to fix that now. So first things first is let's do this on the bottom trace. Bearing in mind these are going to be plated through holes. So I'm broken. I'm broken in the sense that I like to do things in the most complicated ways. For example, I have this project. Let me just switch it off and back on again so I can showcase it. So this is a streaming controller, like the Elgato Stream Deck, that I have built myself. And this deck, and if I boot this up, this takes an e-ink display and connects to my broadcast software. And the cool thing about this is that I can disconnect. I can place this on my arm. And now I can control my stream from my arm, and I can change scenes. I can do all the things with this. Now, the cool thing about this device is that when I go to a convention, so I go to Maker Central in the Birmingham NEC. That'll be in May. I've live streamed from that. I've live streamed from that event for the last 3 events. I've been to every single Maker Central, and I control the stream from this device. It's Pip-Boy, right? Although not as heavyweight as a Pip-Boy, right? Pip-Boy would be an absolute nightmare, right? Something that size. Actually, I think I might put this on backwards. Have I put it on backwards? I believe I have. Oh, no, I haven't. I have not. But yeah, it's there we go. Cool. But yeah, it's gone through a series of iterations. The original cheap deck was named because it was incredibly inexpensive. It's no longer incredibly inexpensive. But this is the original cheap deck. This is what I used to control my stream with back in the day. So it's gone through a series of iterations. We're now on version 2.1. There will be a version 3 coming out. And the version 3, I will actually be making a commercial product. I will more than likely either go through pre-orders or I will do a Kickstarter for version 3. Anyway, we kind of sidetracked, but I thought it was useful to give some context as to why it'd be even more compact, right? So right now, I'm in the process of building a Lumen PMP, pick and place machine, for automated circuit boards. You've got to make or buy one of those silent mode, right? I hear you, man. There will be options. There will be options. So yeah, like I say, the cool thing about this is that it completely frees me from my desk. I can go to the workshop downstairs and get on the laser cutter onto the CNC, and you know, I've got full control of the stream from this location, right? So back to what we were talking about. Let's go here. So what I'm going to do is I'm going to do a copper fill. And I'm going to do a copper fill for the 12 volt rail. So let's have a look. We want a filled zone. And we'll start the filled zone here. We're going to choose the... all right, cancel. We need to change this to the bottom copper layer. And we are going to go for the copper fill. Boop. And then we're going to draw a line. So we want this to be on the blue line here. Yeah. So we're on the bottom of the board. And we're going to switch from what is currently selected to channel A. We're going to change that to 12 volts. And we're going to just run this box around this main 12 volt input. Okay, so we've got that going on here, okay? So when I do the DLC check, the design rules check, let's do that now, and then we hit run, what's going to happen is this blue area is going to get filled in, right? So now, instead of this puny little trace attempting to carry, like, up to, what, 4 amps in certain circumstances, you know, that trace would just become a fuse and we'd have the magic smoke. And we don't want that. So let's close that, and we're going to click this wire, and we're going to just drag this trace into this zone here, right? So now we've got this broad copper fill area that's going to deliver 12 volts to all of these pins. Just to make doubly sure that we've got it, what I'm also going to do is I'm going to do a copper fill on the top layer, right? Again, for 12 volts. So we're going to duplicate this process just to make sure that we've got plenty of coverage. This is probably overkill, but, you know, we've already had the voltage regulators say good night to us. So let's see what we can do here. To prevent that happening again. All right, so let's do the design rules check again. We'll run the DLC, and now we've got a copper fill on both the top and bottom. There should be plenty of copper to handle the loads that I'm going to be putting through this. So now we've got to figure out whether or not there are any missed traces. Okay, now KiCAD can be a little bit hit and miss in telling you whether you've missed something. Right, so let's do the design rules check. Okay, and then we're looking for unconnected items, and there is nothing here to say items are unconnected. Oh, IMC, you're very welcome. So like I say, I'm live streaming on Twitch and YouTube. So if you are on YouTube and want to find me on Twitch, it's twitch.tv/IQ Workshop. And on YouTube, it's YouTube/IQ Workshop. We're gunning for the old vanity metric of monetization on YouTube. So feel free to hit that subscribe button and watch a lot of content. If there's anything that you guys want to see, feel free to hit me up in the comments. On that point, if you're watching on YouTube and you either want to put this in the chat or in the comments of the video, comment on what problems you have encountered. Thank you so much for the follow or subscribe on YouTube. I keep getting those words mixed up because they should just synchronize what those things are, right? So it's a subscription on YouTube and a follow on Twitch. A subscription on Twitch costs money, but doesn't on YouTube. Oh, content creation. It's fun. It hurts my brain. And I swear I'm undiagnosed ADHD. But anyway, so point being made. It's gone. Somebody remind me. Oh yes, comment in the description in the comments of the YouTube video problems that you've encountered and how you solved them. I'm keen to hear what you've got to say. At this moment in time, I probably would prefer YouTube because there's a watch-hour metric that we're currently going for. To achieve monetization, you have to have at least 1,000 subscribers, and you need a minimum of 3,000 watch hours to unlock the first tier of monetization, which is super chats and memberships. You need 4,000 in total to unlock the main what everyone knows historically as YouTube Partner Program. That's what we're shooting for. We'd like to see that, but I appreciate everybody hanging out. You guys are awesome. So we are not out of the woods here. We've got 19 warnings and we've got 10 errors. So let's just make doubly sure that we do not have any missing traces. And we do that by turning off all of the layers, right? I'm going to switch off all the layers. Everything is going to be gone. So all that, I don't think there's an option to deselect all of these in one hit. Keep going, keep going, keep going, keep going. Right, they're all gone, right? I'm going to turn on the top copper layer, and I'm going to delete a trace on purpose, right? I want to generate an error, right? So I'm going to delete that. And you can see there's this blue wire between these 2 points. So when I turn off the top copper layer, this blue wire remains, right? So even though there are no traces, we can hunt down things that are not connected, like ground wires. I'm saying nothing, but you know, if you know, you know. I can now turn off all of my traces, and I can just do an inspection around here to see if I can spot any blue wires indicating we have disconnected traces. Okay, so these red things, these are errors. These are things that we need to take a look at and potentially take action on. These yellow markers, these markers are telling us that there is a warning, right? You take a look at it, it's not the end of the world, but strictly speaking, it's not right. I'm a hobbyist. I'm not an electrical engineer. I am not going to be, building motherboards for a living. So for my projects that I want to do, that's fine. Just know where you are in the process of things. There is a rabbit hole that you can go down, trust me. Not a low barrier to entry. About us? No, I hear you, man. I hear you. It is effort. And we're creeping closer to the monetization, the first level monetization. We're about halfway. We're about 1,500 watch hours at the moment to tier 1 monetization. So, hence the live streams. Hey, Hayden. Welcome, welcome. I think I might have seen you somewhere before, but the names are different. But I'm putting 2 and 2 together here and might be getting 6. All right. So let's just quickly check over our traces. So these small traces here are just data. They're just triggers. They don't carry high current. So they're going to be going down to the MOSFETs. They're also going to be going to the LEDs. So that's pretty cool. I'm happy with those. All right. So let's take a look at our inventory of errors, right? These are the first things that we need to get into. So run the DRC, and we just unchecked the warnings, and we just left with the errors. So we got 10 errors to resolve. Now, you'd think that the auto router would have abided by the design rules, but it might be that, you know, it's not happy. Okay. All right. So first one is my fault. Okay. So I have placed my ESP32 too flipping close. I put it too close to this hole. I should have spotted that before running the auto router. What an absolute plum. Okay. So we need to fix that. How do we fix it? Well, you guessed it. Global deletion of traces and vias. All right. So we now select our ESP32, and we're going to get it so it doesn't violate the parameters of the hole. And I'm going to reverse this connector, J3. I'm going to put it on the other side of the board so that the silk screen doesn't appear underneath. So all I do is select the component. So it's like that, and then press F to flip. And it's now on the bottom side. Seriously? Okay. Thinky think. I just need to check something. Let's check this in 3D view a moment. I want to make sure that my text is where I think it is. It is. Oh, that's fine. I can ignore it. What an absolute idiot. But my capacitor and my silk screen for my U1 is now encroaching on pads. So we do need to fix that. So let's do that while we've spotted it, right? So you'll see that was one of the warnings. So we'll bring the C1 to there, and the U1, I'll put it there. Okay, so when we run the design rules check now, we'll have fewer warnings. So the warnings have gone from 19 down to 14, so that's good. Right, so we still got our fill in place. Let us run the auto router and let it do its thing. It's going to pop up on the other screen. Tidecrafter, welcome in. How you doing? I'm going to cancel that and bring that onto screen so you guys can see it. And then we're going to run it. You can see all the air wires, right? You can see all the air wires. This is called a rat's nest. That's the technical term for it. Here we go. It's building the routes for the wires now. We're looking at it's on the second pass. Hey, Libri, thank you so much. Well, yeah, I think it's really important that we show, the failures. There's a lot of, you learn so much more in failure than you do in just pure success. And what we have here is my project took a left turn because of one single component, and that component was a voltage regulator. It was rated for 16 volts, and either I didn't read the data sheet properly, or the component isn't actually rated for the volts that we're intending on throwing at it. It decided to eat itself. So what is the auto route? So Road Rally Race auto route, I think that's likely to be a satirical question, but auto router, essentially what it does is it attempts to connect all of the pads with wires based upon your design. There are a series of rules that you can have associated with traces. These are called net lists. So you can say like a power rail has like a really thick trace, but a signal rail is quite thin because it doesn't carry much current. So this is just building out the circuit based upon our rules, based upon the rules that we applied. So I'm going to do, that's complete. It seems to have finished. The chances are that it's got everything. So let us just quickly do a DRC check. Okay, we got 3 errors. Well, that's an improvement in the number of errors straight away, right? And we got 14 warnings. So the 14 warnings were there before, so that is absolutely fine. Let us select all of these layers and just turn them off. I want to look for unrooted because I've been bitten by this, right? So once bitten, twice shy and all that. I'm going to switch off all of these layers and I'm going to hunt down any unrooted traces. And once I've done that, I can be certain that I don't have any problems. So I'm just scanning backwards and forwards, looking for any blue traces. Alibri, if you're in chat, just a heads up. There was a question around Mac and Linux versions of Alibri Atom 3D in the video that I did. I don't know whether you want to make an official post in there. I did reply to the comment. I did ask. I did state that I would probably be reaching out for an official answer. But if somebody could go and take a look at that, that would be awesome. And that would have been within the last 3 days, 2-3 days. Cool. Right, so our auto route, that is done. Let's switch off, or switch on, should I say, the layers. There we go, there we go. All right. Let's quickly do a DRC check. And we'll get into the final 3 errors that we have for this board. Okay, thermal. Okay, so it's telling me the first error is that a thermal relief is incomplete. Are we really that worried about it? Right, so let's look at that. So that means that this pad here, right? It's got these 2 thermal reliefs, but it doesn't have a north-south thermal relief. Probably because the design rules checker is saying it's forbidden. It can't run a trace through here and put the thermal relief in top and bottom because the pads are just too close, which is fine. I think we can ignore that. Okay, so that is, it's that fill to that pad. So that's cool. I'm cool with that. It looks to be the same story for pad 4. So 2 and 4, and no doubt 6 is the same. So they're the 3 errors, right? That the thermal relief is not sufficient to supply voltage, you know, through, especially at any level. You know, it's saying it's not complete, which is absolutely fine because we've got a fill on top and bottom of this section, right? So we should have more than enough thermal relief and still be able to give the current that we need to give it. Let's have a look at the warnings that we've got. So let's uncheck that. And these are probably going to be things like line, there we go, line on edge cuts. Right, so my J1 is like off the board. So let's put it on the board. So now when I run DRC, we should go down to 13. And we do. Let's do the next one. J3. Okay, so it looks like J3 is encroaching on the courtyard, is it? Okay, warning, footprint. Let's expand this. Does not match the copy in the library. The reason it doesn't match the copy in the library is because I've removed the 3D model from this set of pins, I believe. So that I'm not overly worried about. So I'm just gonna choose to ignore that. Okay, what do we got here? Channel, right, PCBX, channel 4, low voltage controller on silkscreen. Thickness of out of range, true type font, character stroke weight. It's complaining about the font that I'm using for that piece of text. That's fine. I'm going to ignore that as well. And the IQworkshop.com silkscreen. That's fine. That's fine. A out of range board setup constraint silk text height minimum height 0.8. That's fine. It's complaining about the fonts for the silkscreen. So that's like nothing to really write home about. Okay, so I think if we close this and we'll save the file, we are now in a position to look at this in 3D. And there is our board. Notice we've got a bit of text here that says FID2. We've got to get rid of that. We do need to get rid of that. I don't want the fiducial text. We know what it is. We know what you are. We just don't want you there. What I'm going to do is I'm going to add some silkscreen text. Okay. And we say 12V max. All right. Click on OK. And we're going to stick that text right by there. So we're warning everybody that this is a 12 volt maximum board. If you put more than 12 volts in it, you can probably put up to 16 volts. So there's a little bit of headroom, which is always good to have. But you don't want to put any more than 12 volts into this. Otherwise, you're likely to see the magic smoke. All right. Yeah, you're risking it, right? You're risking it for a biscuit. You'll see. You see on J3, I've got no pin headers there. Technically, I won't have pin headers here either. In fact, let's just make this look like it's going to. So if I go into this component, escape, escapee. Right, double click. And let's go into 3D models and then just uncheck the show option. Click OK, click save. We'll get another error in the DRC to say that the model doesn't match because we just switched off the 3D elements of it, but that's okay because we're not installing pin headers. We just want the footprints. So that is what the board is going to look like. We managed to shoehorn that voltage regulator in there. That's good. So all I've got to do now is output the Gerber files, the manufacturing files, and get this board reordered. And we should be, in theory, good to go. Tell you one thing I will do. I'm going to check the trace width that's coming down to my LED. And I just want to make sure the current draw from an LED, a single LED, is going to be fine hanging off these thin traces. If I need to beef the traces up, I can do that with a netlist update. But other than that, we should have fixed the problem that we had previously. So we should no longer have, just to summarize, we should no longer have this go on, right? Smoky, smoky. You might even see pearly gates and clouds. Unlikely with 12 volts. Let's say, I mean, just remember, it's not the voltage that kills you, it's the amperage, right? 1 amp will kill you. Now, the reason that low voltage is considered safe is that it doesn't conduct that well through the human body, through the skin. I don't know if it's the technical term is skin effect or what. I'm not entirely sure, to be brutally honest. So don't quote me here. But you could stick, you can stick your tongue on a 9-volt square cell and feel the tingle, right? And there could be quite a lot of current going between those 2 points, but it doesn't hurt you per se. It doesn't cause physical harm. But yeah, it's the amperage that kills you, not the voltage. But no, you're unlikely to have a major problem with 12 volts, which is why I am more than happy to build and release a 12-volt board. Once we've ironed out the bugs, this will be going up on my shop, on my website, theiqworkshop.com, and we will make this available as a physical product should somebody want to use this in their own applications. You can use Tasmotor on its own. It has a web interface that you can switch things on and off. You can integrate with HomeAssistant, so you can create complicated automation scenes. It's really cool. But yeah, we can handle up to 4 channels, and this is overkill for the project, really, because I only need 1 channel per light. But this is good exercise in creating circuits and to practical fault finding, right? So I'm really pleased. Okay. A couple of milliamps across the heart is enough to send you to beyond the veil, right? Exactly. It's the current that kills you, not the voltage. Well, it's not a great idea to watch YouTube in the booth with a tablet or a laptop, because there's some like high voltage components which helps the conductivity a lot. So yeah. All good. So we hit the save button on this project and we are done. Right then, guys, I'm going to call it quits. We have overrun slightly, but I'm more than happy to, because we've had some good chat. And we've also had a good result in getting these boards refactored. So I'm going to keep these boards as a little memento and a little reminder to always check the datasheet, because there could be some information in there that you need that will tell you why your project has decided to eat itself. More than likely that you've used the wrong component. So, until next time, the next live stream will probably be covering off some board assembly. I've got some work to do in the next 7 days. To do some hardware shakedown on a more complicated project. I'm not sure if I can say what that is just yet, but it will be coming soon. I will be doing a live stream where I will be putting together a panel of circuit boards, and we're going to reflow them in the oven. But I do need to get this technical validation of the release candidate board done. Thank you, Badass. Thank you, Buck Naked on Twitch. Road Rally Race, appreciate you, buddy. Dimitri, thanks you on YouTube. Did I want to raid on Twitch? When I'm going to order the new boards, I probably will do some validation of those thin traces tomorrow, because I don't think that there's thin traces on... Oh, there may be. There may be thin traces on this board. I will double check the trace width just to make sure that the current for the LEDs that are going to be on board are, it's sufficient. It's going to handle them, right? But then it's either going to be tomorrow or Wednesday. Yeah, tomorrow or Wednesday I'll likely place the order for those boards and get those out. Sooner it's out, sooner it's back, and then we can get on with it. But yes, as I was saying, there's going to be an upcoming stream where we're going to be assembling PCBs There's going to be like lots of small components going on boards like this. And then we're going to go and use my reflow oven. Let me just give you a quick sneaky peek. I've got to do a video on my reflow oven on how I put it together. Where are we? What have I done, Buck? Did you not hear me? You need two of me. Is that better? Yeah, dang it. So yeah, we've got a toaster oven that I've converted using this control unit into a reflow oven, and I can now solder like a panel of circuit boards. So I'll be able to do like 14 circuit boards or so in one fail swoop. So bingo, right? This is gonna be awesome. This is the Lumen PMP. I got to get back onto this because this does need to get completed. I got a motherboard to make for it. I've got the head assembly to get the components for and put together. I've got 2 of the 3 linear rails connected with belts. I've got cameras to get. I've got to take these plates. I've got to get these plates off, and I've got to put them on the CNC machine to drill them out and cut the slots. There's lots of things that got to get done, right? Right. So, Buck, keep an eye out. Keep an eye out for the video on how I put my reflow oven together. Hit me up in Discord, and we will we'll have a bit of a chat around how I put that together. The controller came from a content creator from Australia, and I gotta be fair, it's the business. Right then, guys, I'm not gonna raid out onto Twitch, so there's something called raiding on Twitch, and that's where you end your stream and you take your audience somewhere else. Because we're live streaming on both platforms tonight, I'm gonna call it quits, and we'll end the stream without the raid. But thanks for the suggestion, Buck Naked. Appreciate it. It is now. KiCAD, I'm not quite sure the context of that comment. So I'll give it a second to see if you want to reply. But yeah, that comment has come in mid-flow of a sentence, and I now don't know what that means. Anyway. Right then, guys. Until next time, have fun, be safe, and don't forget, it's not the end of the world if you make a mistake. You can always problem solve it and move on and learn everything, right, along the way. Yeah, right. It is. It is the business, KiCAD. You're right. You're right. Thank you for adding the context. Yes. I've got a lot of circuit boards to make. This week's a big week. So watch this space. You do it. Thanks for lurking. I appreciate you, man. You take care. Everybody have a great day. Have a great night, no matter where you are. Until next time. Bye for now.